Geometry lesson, perimeter and area on the coordinate plane. So we will be working on the perimeter of this particular shape. So since we have no idea what this is, let's give it a rough picture, shape of what this is. So we could get our bearing. And we already know that when you go around the shape, it'll be PQRS, right? So that's 2, 5. Should be 1, 2, 1, 2, 3, 4, 5. It's around here somewhere. Because I have the value here, so I'm not going to bother writing it. It'll just be a lot of clutter. And Q is -3, 0, which is 1, 2, 3. It's about here. Let's see. R is 2, -5. Ooh, same distance. So we know that because this is 2 and a 5 and 2 and a 5 in the negative direction, that distance is the same. And this is the midpoint of that, so it looks like this has to be the same, right? So you have to sort of think about stuff like this as you're doing it. And that's a 6, 0. That's about 2, 3, 4, 5, 6 right there. So that is S. So when I connect these, I feel like this is a... I'm just going to make a, wild guess over here. That this length and this length is the same, okay? And the distance from this way and this way is the same, so this two are the same. The question is, are these two the same? Okay, so that's a 2, and that is -3. So distance over here is 5. And then S is 6, so distance here is 4. So no, they're not the same. So I could clearly see that these two are the same, and these two are the same, right? All right, guys, let's get started. Okay. So I need to find PQ, right? So PQ squared. So distance between PQ. So we've been doing this lately, right? Change in x squared plus change in y squared. Like this, right? And the change in x is 2 minus 3, which is 3. And then the y's are 5 minus 0, right? So that's both 25 plus 25 is what? Twice the 25? There's a reason why I did that, because when you do PQ square both sides, like this, that perfect square pops out, right? To be 5 root 2. So if you're looking for that value only, that's what you would do, right? It's asking us to round to the nearest tenth. We'll do that at the very, very end. Okay, so we found PQ and then hold on, and PQR. Okay, I don't know why I wrote it that way. Sorry about that. So that is R, and the RQ should be the same, right? So I won't do that. So let's find PS. And what you could do instead, you could do the distance formula square root this way. Okay. So I'm giving you the freedom to do it either this way, using Pythagorean theorem, or as distance formula. But as we all know, distance formula is nothing more than a variation of a Pythagorean theorem. So we need change of x squared plus change in y squared. Okay. So this part that I'm doing is more for instructive purposes. You need not add that step. All right. You don't have to. But if it makes you feel better, you should. So we're looking for PS, the distance from here. So this is 2, 5, and that is 6, 0, right? So change in x is 6 minus 2, which is squared. And then y is 5 minus 0 squared. In this particular case, I actually made a little boo-boo. You really should keep the order in which we do this, even though it really doesn't matter in this particular case. So that's a 4 squared, which is what? 16. And that is a 5 squared, which is 25. And that is root 41. Do you see that? So, yeah. So that's it. Okay. So now we're going to find the perimeter. So we know that the perimeter, the whole thing, perimeter, has twice the PQ and twice the PS. right? Because PQ and RQ is the same, PS and R is the same. So I'm going to add these two and I'm going to double it. Now, if you notice, you could do this a couple different ways, right? So to find the exact answer, that is 5 root 2 plus root 41. And that right there is 10 root 2. Oopsie. Let me write a little slightly neater. 10 root 2 plus 2 root 41. To get this answer, I would prefer to see this answer right here, guys. And then even when they're asking for the rounding answer, I like to see the radicals first. And putting that into the calculator, it should come out to 26.9. Now, I've seen so many times many of the students who just rely on the calculator strictly and get this one wrong. So how can we estimate this, right? All right, so this is extra material. So let me put that in green. So this distance right here is actually root 50. How much is that? So this is estimation. Root 50 is between root 49 and root 64. So root 50 is between 7 and 8. But it is so much closer to what? 7, right? It's probably about 7, right? All right, let me bring this down just a tiny bit. And then how about root 41? Is between root 49 and root 36. And that's between 6 and 7. But if you think about it, the gap between 41 and 49 is 8. And the gap between these two is 5. So chances are it's slightly closer to 7, maybe 6.5, 6.6. So I'm going to estimate that the perimeter is approximately double 7.1 plus 6.5, or maybe even 6.6, right? And that gives you 13.7. When you double that, that's going to give you 27.4, right? So I just did a rough estimate in my head. It's pretty close to the what we got in the calculator, right? Now, remember, I estimated that, and I estimated that. So I'm adding two estimates, and I'm doubling it. So you're doubling the estimation, right? So that's not too bad. So I know it's within the range, right? So being able to do this is probably a good idea. But this right here is not necessary, right? But certainly very helpful. Okay, guys? All right, guys. So that was a slightly beyond the scope of this class, but I thought you might enjoy it. Okay, so let's look at some formulas here, guys. Finding the area of figures in the coordinate plane, right? So triangle. Why is that? So the area for that is 1/2 base times the height, and the rectangle is the base times the height, and parallelogram is base times the height. So I'm going to do a quick way to remember how to do all three of these. Okay, guys? You guys ready? All right. So rectangle, we all know, right? So that will be our starting point. And when you have a parallelogram, it looks something like this. So they're parallel. But what if I draw a vertical line this way and this way? What do you notice, guys? You notice that this area right there and this area appears to be the same. So if you cut that and move this over here, we'll end up with this shape. And that's the base and the height. Exactly. So that way you could tell that the area of the parallelogram, right, as long as the base and the height is the same, is same thing as the equation for the rectangle. Because when you cut this piece and move it over here, you end up with a rectangle. Sounds good? All right. The y is triangle 1/2 base times the height. Well, if you sort of think about that for a sec, okay? Let's do that with green, okay? Why is that true? Well, let us say that we have a parallelogram, oopsie, like this, and this is a base, and this is the height. Now, if you cut it in half and find this, you know that when you cut across the diagonal like this area of the triangle is 1/2 of the parallelogram. That's right, the area of the triangle is 1/2 of the parallelogram. Not only can you do it that way, I could have cut this thing the other way. As long as you cut across the diagonal, you get the same exact equation. So that area is 1/2 of the area of the parallelogram, which is 1/2 BH. Sounds good? All right. And the next one, let's go with red. These, you could look at it, that particular one in the same way, okay? Which is that the rhombus and the kite, for both of them, the area is 1/2 the product of the diagonals. What you could do is, if you draw a rectangle around it like this, okay? What do you notice, guys? That this right here is 1/2 of this. And carrying that argument, that right there is 1/2 of the upper left, and that right there is the same area as this, right? So taking that argument all the way through, that middle is 1/2 of the outer rectangle. Because that was diagonal 1, the distance from here to here is diagonal 1, and that's diagonal 2, so that's diagonal 2. So the area of the rectangle is the product of the two diagonals, and the rhombus is half of the inside. And then you could make the same exact argument for this right here, guys. Same exact argument, okay? So that occupies half the space of the rectangle circumscribing either the kite or the rhombus. That is the reason why the area for those two is 1/2 of the product of the diagonals. And for those of you guys who did the question of the week and used this particular equation, that was perfectly fine. And we have a trapezoid, and how can we look at that more intuitively, right? And I'll do the derivation right now as well, right? So the way I like to view trapezoid is the following. Okay, I'm gonna maybe zoom in more. Okay, if you drew a rectangle around it like this, okay, what you'll notice is that this right here and this right here and this right there from our past when we do the midpoints, right? Look at this right here, guys. Okay, this area and this area is the same, and this area, hold on, and then cut right to half right there, guys, right? This area is the same as this area. As it turns out, that distance right there is the average of the two bases. That's right. And the height is the same. So to find the area, this rectangle right here, guys, is that times the height. So that's one way to look at it. Okay. All right. There are some other proofs, but I think that is sufficient. Okie dokie. All right. So yeah, that wasn't much of a proof, as more was like an illustration of how it might have been. Okay. But what I can do is, you know what? I think you deserve better. So why don't I give you a slightly more rigorous way of looking at this? Okay. So I'm going to draw this slightly differently. Okay. You guys ready? All right. So when you have some random shape like this, and that is B1, and that here is B2, and the height is H. What we can do is, through this point, I'm going to draw a line that's parallel to this. So like this over here, right? So those two are parallel. So when you do this, and when you do that, we already know that these two are parallel, because by definition of trapezoid, right? So we're drawing a parallelogram inside the trapezoid. That means that the opposite lengths are the same, that's B1. And this distance right here is B2 minus B1, like that. Okay, so we got area 1 and area 2. So far so good? Okay guys, let me move this shape to this side so it creates a little bit of a, what's the word I'm looking for? A little bit of space for me, okay? There you go. How do you find area 1? Well, that's a trapezoid, what is that? A triangle, isn't it? 1/2 the base, which is B2 minus B1 times the height. What is the area of 2? That's just B1 times H, right? Because that is the formula for finding the area of the parallelogram. So the area over here is, the total area is A1 plus A2. So that means we got this. H plus B1 H. Let's distribute this 2 and factor out the H, shall we? All right. When you do that, that's 1/2 B2 minus 1/2 B1 plus B1. But when you look at this part, it's not equal to positive 1/2 B1. So now we're going to factor out the 2. So therefore, the area is B1 plus B2 divided by 2 times the height. This is actually the way I prefer to write it, because it sort of reminds me, oopsie, sorry about that, that this equation, right, when you put this together right here, that part right there, is that it's a height times the average of 2 bases, because that's the way I like to think about it, okay? So that is the average of 2 bases. And when you think of it that way, it sort of reminds me of this idea that we just talked about, more intuitive way. All right, guys, so that was an introduction to this. So let's do a couple of examples, and I think we'll be done. Okay? All right, here we go. Let's look at example 10.5.6. Okay? We need to find the area of each figure. Now, we need to utilize the shape, right? Okay, this looks like a parallelogram, isn't it? And you could quickly check that by looking at the slopes over here. So that is 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay, so that is, slope is -2, right? And then over here, and then what you could do is, if this is like on a physical space and you have a ruler, right? One of the things you could do is kind of do this. It's kind of like, it's not really math, but it's something that you should probably do. And if you have a ruler like that, you could just slide it down like this, and to see if they're parallel, and the length is the same. And I just showed you that it is, right? But the way that you could really do this is that this is 3, and this is 6. So, and then this is 6, and that is 3. So you know that distance here has to be the same, right? All right, how about here? 1, 2, 3, 4, 1, 2, 3. So that is 3 and a 4, and I got 3 and a 4. So we know that these two are the same. All right, so we definitely know, confirm that PQRS is a parallelogram. So the area, and some of the shorthand for writing the area is putting brackets around it. This is the notation that I use. And in some math books, it's not a common notation, but you could do it this way if you like. Or literally say that area of the quadrilateral PQRS. Okay? So we know that it's base times the height. Look at this. What's my base? Okay, so let me erase this part, because I need clean area now, right? My base is PQ. That's my base. And that right there is my height. Okay? Okay. So now I'm going to do that work on the side here. What is my PQ? Is a square root of, and we found that was 3 and 6 earlier, right? So 3 squared plus 6 squared. So when I do that, what do I get? So that is 9 plus 36, which is what? 45? Oopsie, what just happened? Sorry about that, guys. There you go. So let me just zoom that just for a tiny bit. So that's 45. And that's 9 times 5. 9 pops out as what? 3 root 5. We good? All right. And then what else do I have? And this thing already gave you the how to find the height right there, because it has to be perpendicular, right? But what if it wasn't given to you? Well, this slope and this slope has to be perpendicular, right? We know that the slope of PQ was what? -2 from earlier calculation, right? Remember, that was 3 and that was 6. It's going in the negative direction. So we know that, to get a perpendicular, slope of ST has to be negative reciprocal, which is half. So from here, what I could do is just keep going half, 2 to the right, 1 up, 2 to the right, 1 up. And it just happens to be perfect. And that distance right there is 4 and 2. Do you see that, guys? So the ST is square root of, the change in y is 2 squared. Change in x squared is 4 squared. So that is 4 plus 16. And that's root 20. That's 4 times 5. 2 pops out. That's 2 root 5. Is it not? I think so. So now the base, in this, which is PQ by the way, is 3 root 5 times the height is 2 root 5. So that's like 3 times 2 times root 5 times root 5 by rearranging them, right? So that's 6 times 5, which is 30. So the area of the PQRS, therefore, is 30. Did that work for you guys? All right. You know what? That is too red. I generally don't like to put too... Okay, sorry about that. Let me just change color to the blue. There you go. And so that differentiates from the previous material. Okay. All right, guys. So here's a little like doohickey that we have to study. How do you find the area of composite figures? Okay. So the composite figure is made up of simple shapes, such as triangle, rectangle, and parallelogram. To find the area of the composite figure, we need to find the area of the simple shapes, then use the area addition postulate. It basically means that you could just add the areas together. That's not overlapping, right? And you could use the area addition postulate to find the area of the composite figure. Well, sounds like I said the same thing like 2 or 3 times already, right? So the area of the region is equal to the sum of the areas of non-overlapping parts. In other words, let me just give you a visual. So if you have this particular area, and there is a way for you to find the area of area 1 and area 2, so the total area is area 1 plus area 2. Okay? Sounds good? All right, guys. So I will do, I could do 2 examples. Okay? So this one we're going to do by addition, the other one we're going to do by subtraction. Okay? All right. What's a good way to do this? It looks like, if I'm not mistaken, if I draw a line this way, let me use the blue, going from here to here like this, right? It looks like it's a rectangle and a triangle. Let's check it out. The slope over here is what? NM, that is 1, 2, 3, 4, 5, 6, 1, 2, 3. Okay, we know that the slope of NM is 1/2. What is the slope of JL? 1, 2, 3, 4, 5, 6, 1, 2, 3. Oh, it's the same. So the slope, okay, I could even do it this way, right? So they're both the same. Slope of JL, they're both the same, so they're parallel. That implies that NM is parallel to JL. And so what is the slope of NJ, right? And I know it's negative, so even before I begin, I know it's negative. And then that is 1, 2, 3, 4, 1, 2. That's 4 and a 2. Change y and change in x. That is 4 over 2, which is 2, but it's negative. There you go. All right, guys? All right. What is the slope of ML? That is 1, 2, 1, 2, 3, 4. So over there, change in y and change in x, we know it's negative. Y changed 4 times, x changed that, so that's negative 2. Yeah, they're both the same. And then visually, we could tell that because these two are negative reciprocal of each other, then they're rectangles, right? All right, guys. So we know that, so let's just do this one more time. Nm times nj is 1/2 times negative 2 is negative 1. So it's a right angle, isn't it? Right. I should use ml, not nj, my bad. So ml, so yeah, so they're perpendicular. So that implies the nm is perpendicular to ml. So therefore, it's a rectangle. Okay, good. How about this one over here, guys? So this is a triangle. So I think this will be our base right there. I need to know that length, and I need to know that length right there. And then I need to know this height right here, right? Let's see if we could do that easily. So we know that that is 1/2. So I have to go negative half. Let's see if we could find a nice, I'm just going to draw a nice, there you go. So from here, I want to draw negative half, which goes up 2, left 1. Beautiful. It intersects right here beautifully. Okay. So now our job is to, sorry, let me make that a little smaller. I was writing a little bit too big, right? So from that information, we could say that JLMN is a rectangle. Okay. So in order to find the area of that, I need to find this length and this length, right? Let's do that. What does JL equal to? JL is a square root of, earlier we found that this was what? 1, 2, 3, 1, 2, 3, 4, 5, 6, right? So the 3 squared and 6 squared. Change in x was 6, and change in y was that, not a 3. So that's 9 plus 36, which is root 45. Is it not? Yeah. And we've done this particular value earlier. That's equal to 3 root 5. All right. So what is nj? That is 1, 2, 3, 4, 1, 2. So that is 4 squared plus 2 squared, right? So that was a 4 right there, and that was a 2 right there, right? So that's a 16, that's root 20. Oh, wow, this is the same thing as we did earlier. Nice. Okay, and then we need one more value, and let's call this thing, I don't know, x. So kx is a square root of, that distance is what, 2 and a 1? Right, 2 squared, 1 squared, which is root 5. All right, guys. So the area of JLMN, that is a rectangle, isn't it? It's the base times the height. It's this times this, which is these two. So that'll be 3 root 5 times 2 root 5. Earlier we found that to be 30. And the triangle is JKL. Oh, by the way, I'll be moving this down here soon, right? So don't copy me exactly. So 1/2 the base. Base is this one, JL, which is 3 root 5. Times the height, we found it to be root 5. So this part gives you 5 times 3 is 15. It's 15 over 2, which is 7.5. Therefore, so the area, what's that shape? JKL MN, right? The pentagon is the sum of these two values, JLMN rectangle JLMN and triangle JKLN, and that is equal to 30 plus 7.5, which is equal to 37.5. Okay, guys? All right, so this was kind of big. I wrote it kind of big. So what I'll do is make that tiny bit smaller. There you go. Bring it down a bit. Make that a little tighter as well. Kind of goes in there. There you go. And make it a little thicker. And then I'm going to box the answer that we came up with. There you go. Okay. So that is the phase 1. Phase number 2, finding all the lengths, putting it all together, finding the individual shape that makes up the composite figure, and that's a step number 4, putting it all together. Okay, so that's how you add the shape. So all we did was we added the rectangle plus the triangle. Now in the second method, they're asking you, how do you find the area using the subtraction method? So what you could do is find the area that's easy to calculate and subtract the rest. Okay. Before we begin, what do we notice, guys? We are actually looking for this area right here, the inside. Okay, let me shade the ones we're looking for. Right there. That's what we're looking for, right? But do you notice anything that's interesting about this shape? Right. That the top half and the bottom half look the same. So we don't have to do both of them. We could just do one of them and then double. Okay. All right. So what we could do for the bottom piece is the following. So now that we agree, let's get rid of that shape, right? Okay, so how can I find this area? Let me just block it off, actually. So this area is what we're looking for, right? But it's not easy to find that area and then subtract that off. Right. So the area 1. So what is area 1 equal to? Area 1 is equal to outer rectangle minus the triangle. It is the rectangle minus the triangle. And that one should be pretty straightforward, right? We could just count. 1, 2, 3, 4, 5. The base is 5. The height is 1, 2, 3. Okay, let's look at this triangle right here. The height over there is 1, 2, 3. That's 3 right there, and that is a 2. So that's 1/2 times 3 times 2. So that is 15. They cancel. Minus 3 is 12. So the area 1 is equal to 12. Let's look at area. Let's get area 2. The area 2 is if you could draw a shape like this, right? What we could do is take away these 3 triangles, shall we? All right. So the area 2 is the large rectangle minus the 3 triangles, T1, T2, T3. All right. The large rectangle is 1, 2, 3, 4, 5. So that's 5 over here. 1, 2, 3, 4, 5. So that's 5 right there. So I'm going to plug it in. So that is 25. So let's get triangle 1. That's triangle 1, guys. Height is 2, 1, 2, 3. So that is 1/2 times 2 times 3, which is 3. And this right here, triangle 2. The base is 2, 1, 2, 3. Same thing. That's 2 and a 3. So 1/2 times 2 times 3 is 3. That right there is triangle 3. 1, 2, 1, 2, 3. Oh, it's the same. So all 3 triangles are 3. So that's 3 plus 3 plus 3, which is 9. Subtract that from 25. We end up with 16. But the total area, right? Total area is area 1 plus area 2. And that is 12 plus 16, which is 28. Looks good. All right, guys. So in one of them, we did the calculation by addition. In the second one, we did by subtraction, right? And the other is a difference in notation. So when you have a bracket, it means that it's area of the polygon JKLMN. On the right hand side, I didn't do that, did I? I mean, you could have, but I just want to show you that both are acceptable. All right, guys? All right, so let's move on to your turn. So there are 3 questions, number 4, 6, and 7 from your textbook. Do me a favor, pause the video and try this on your own. Okay, guys, I'm going to assume that you've already done that. Here are the answers. Here are the solutions. Here we go. I'm not going to walk you through it. It's very similar. So if you had a question, we'll talk about it in class. Here are the next 2. All right, guys. That's it for today. And I'll see you in the next video. Have a good night.